Our next topic is epsilon net. Let XD be a metric space and A is subset of X. Then what is epsilon net? If epsilon is some positive number, arbitrary positive number, the epsilon net is all X belongs to capital X such that distance between X and Y less than epsilon for every Y belongs to A. So this is called a epsilon net for A. Or we can also say that a set M epsilon, which is part of X, is called a epsilon net for A if there exists a point X belongs to M epsilon such that distance between X and Y less than epsilon for every Y belongs to A. So this is a definition of epsilon net. So basically, what is this? Basically, epsilon net contains all those points whose distance from whose distance from this set A is very small, whose distance from this set A is epsilon, right? So this is a contains all those points whose distance from A is less than epsilon, right? So this is a epsilon net. Epsilon net contains only it is epsilon net for A. Clear? I repeat again. It is a epsilon net for set A. It contains those points whose distance from A is small, whose distance from A is epsilon. Clear? So this is the epsilon net for A. Now, this is very important definition, total boundedness. We already read that compact set. So what are the compact set? We know that every open cover, if every open cover of set has finite subcover, then it is called a compact set. Now here in total boundedness, if there exists, if there is a finite open cover of set, in this case we used open ball, not for open set. For example, the definition, I let XD be a metric space and epsilon greater than 0 be given. That's the set A part of X is said to be totally bounded. If for every epsilon greater than 0, there exists a finite epsilon net M epsilon, which is part of X. So there is one definition. And the same definition is, so we remember this definition basically. The set A part of X is said to be totally bounded if for every epsilon greater than 0, there exists a finite many open balls Bx1 epsilon, Bx2 epsilon, Bxn epsilon, such that A is contained in this union. It means if there are finite balls which cover the set A, then A is totally bounded. So very in simple way, if set A is covered by finite balls, then A is called total boundedness. So simple definition of total boundedness is if it is A is called total boundedness if it is covered by union of finite balls. if it is covered by union of, if it is covered by finite union of a ball, or we can say that it is covered by finite ball, then it is called a totally bounded set. In compact set is covered by finite open set. In this case, A is totally bounded set is covered by finite open ball, right? So that is the difference between compact set and total bounded set. So these point x1, x2, xn, these are basically point of epsilon net, m epsilon. Clear? Because these points are finite, so m epsilon is finite. Now, in this way, so it is a definition of total bounded set. Now, this is very important result. Let XD be a metric space. If subset of A is relatively compact, then it implies A is totally bounded. It means relatively compact space are always totally bounded, but converse is not clear. So relatively compact implies totally bounded, but converse is not true. Converse is true in some other condition. That is, in complete metric space, converse is also true. But in normal metric space, only relative compact metric space are totally bounded. Now, suppose A is relatively compact, then by definition, its closure is compact. Now, our purpose is to prove that this set is totally bounded. Then simple meaning A is covered by finite ball. That's all. So our simple purpose is A is covered by finite union of open ball. Open ball, open sphere, open neighborhood. We can use open ball, open sphere, open neighborhood. Now, if A is empty set, then we have nothing to prove. So it is automatically true result. Suppose A is not empty. If A is not empty, then it means there exists at least one point from this set. There exists x1 belongs to A. Clear? That x1 belongs to A. That x1 belongs to A. If it belongs to, if distance between x1 and y less than epsilon. So our aim is to prove this result. Clear? That is our aim that we want to prove, right? If A is empty, then we have nothing to prove. Suppose A is non-empty, so there exists some x belongs to A. Clear? If this point, if distance of all point A with this point is less than epsilon, if less than epsilon, then clearly A is contained in only one ball x1 whose center is x1 and radius is epsilon, right? Then it implies x1 is epsilon net for A. Our result is true. X1 is epsilon net for A means A is contained in a ball whose center is x1 and radius is epsilon. That's all. It means A is contained in only one ball. Otherwise, if it does not happen, otherwise, then there exists some x2 belongs to A which does not satisfy this condition. At least there exists at least one member which does not satisfy this condition. If all the member of A satisfied this condition, then our result is true. And in that case, this set is epsilon net. But if this condition is not satisfied, by all these members, then it means at least one element belongs to A which does not satisfy this condition. What is that element? Suppose that element is x2. Otherwise, x2 belongs to A that does not satisfy this condition. If it does not satisfy this condition, then it means distance between x2 and x1 greater than equal to epsilon. Then it means distance between x2 and x1 is greater than epsilon. Clear? Now, it means, it means now we take a ball with center x2. Next step. Again, we repeat the same process. If this distance, if this x2 comma y less than epsilon for y belongs to A, then x1 and x2 is epsilon hat. So we add second ball. So first ball, our condition are not satisfied with first ball, then we add second ball. Now, if our condition are satisfied with these two balls, one with center x1, second is when center x2. If it is not satisfied, if it is not satisfied, then again we have x3 belongs to A such that dx3 comma y, the dx3 comma y for y belongs to A, then this is a epsilon net. So this is epsilon net. Clear? Otherwise, otherwise continue the process. Otherwise continues the process. So simple idea, again, a basic idea of this theorem is if A is contained in first ball, then okay. If it does not contained in first ball, we choose second ball with center x2. Then A is contained in x1 ball and x2 ball. If it does not contain in first and second ball, then we choose third ball. Then we choose third ball. If again it does not contained in the third ball, we choose fourth ball. Then we choose fifth ball and continue the process. So continue the process. After finite number of steps, we can find a positive integer n such that x1, x2, xn, this is epsilon net for A. If this is condition, it means A is contained in these finite balls. If it does not happen, otherwise, then again we can find a sequence xj such that distance between xj and xk greater than equal to epsilon, where k is not equal to j. Right? As this, because this, what we get from this distance between x2 and x1 greater than equal to epsilon. And here distance between x3 and here distance between x3 and x3 and x2 is greater than epsilon, right? So similarly, continue the process. The distance between xj, the distance between basically xn plus 1, yeah, xj with x1, x2, x3 and xn greater than equal to epsilon. Clear? It means the sequence xj has not a subsequence which is a Cauchy, because Cauchy sequence satisfied this is less than epsilon. So this sequence does not have a subsequence which is a Cauchy. It means the sequence xj in A has no convergent subsequence, because convergent sequence are Cauchy sequence. So it means in any sequence xj which has no convergent subsequence, because it does not have a Cauchy sequence. If it has no convergent subsequence, then which contradict the relative compactness of A. Why? Because by relative compactness, every sequence has a convergent subsequence. So by compactness, every sequence has a convergent subsequence. So it contradicts the result. If it contradicts the result, then it means this process must be stopped. This process must be stopped. It will not continue. It will stop after finite number of steps. If it will stop after finite number of steps, then it means A is contained in this ball union, this ball union, this ball. Mean A is part of Bx1, Bx2, Bxn epsilon. It means this A is totally bounded. So this is our result. If A is relatively compact, then A is then A is totally bounded. So remember, every relatively compact set are totally bounded. Every relatively compact set are totally bounded, right? So it means relative compact implies totally bounded. But converse is not true. But converse is here. Converse is not true. But converse is true only in complete metric space. Remember, the converse is true only in complete metric space. Otherwise, converse is not true. Clear? So that we will prove in the next result. Thank you.